Hello everyone, let's analyze. So today we're going to talk about essentially the arithmetic we can do with convergent sequences. If we have a couple of convergent sequences and they satisfy certain conditions, what happens when we add, multiply, divide? Can we say something about those sequences and whether they converge? And in fact we can. So let's go through and look at each of these arithmetic operations. So in the first theorem, let's assume that AN and BN are both convergent sequences to A and B respectively. Then the sequence AN plus BN converges to A plus B. Let's prove it. Well, first we have to start with an arbitrary positive epsilon, right? That's always our starting point. Our goal is to show that A plus B satisfies the definition of the limit of the convergent sequence AN plus BN. That means that if n little n is bigger than big N, then the absolute value of the difference between AN plus BN and A plus B is less than our arbitrary epsilon. So there's our goal. That's where we're trying to get to. What do we know? We know AN converges to A. Then the definition of what that means is there is some natural number, let's call it n1, and if little n is greater than or equal to n1, then the difference between AN and A is less than half of epsilon. We also know something similar for Bn. Bn converges to B. The definition of that statement means there is some natural number. We're going to call that natural number n2 so as to not so as to differentiate between n1, right? So n2. And for every n greater than or equal to n2, the absolute value of the difference between Bn minus B is less than half of epsilon. We'll let n3 be either n1 or n2, whichever is bigger. Then if n is greater than or equal to n3, which is greater than or equal to n1 and n2, then both this condition is satisfied and this condition is satisfied. Well, if these two conditions are satisfied, let's analyze what condition this satisfies. So the difference AN plus BN minus A plus B, by triangle, actually by first rearrangement, right? Because of the transitivity of and commutativity of addition, we can rearrange to AN minus A and BN minus B. Triangle equality says we can split that and add a less than or equal to AN minus A and BN minus B. This n is greater than or equal to n3, which is greater than or equal to n1, which means this difference is less than half of epsilon. Similarly, since n is bigger than n3, which is greater than or equal to n2, this difference is less than half of epsilon, which is equal to epsilon. Since epsilon was arbitrary, we've shown that, essentially, we've shown that our goal is true. And just to get comfortable with our math speak, we've shown that for any epsilon greater than 0, there exists a natural number n for which the following is true. If little n is greater than or equal to big N, this implies that the absolute value of the difference of AN plus BN and A plus B is less than epsilon, QED. Now you may have noticed by now that a lot of our convergent proofs have gone this way. We assume two things converge, or we assume that two things are Cauchy, which we now know are equivalent statements, and we use triangle inequality, and half of epsilons appropriately. So by now, hopefully this proof feels familiar to you. And in fact, it would be good practice to practice writing this proof yourself, and to keep doing it until you can reproduce it yourself without looking at the notes or the video. The next result, multiplication. Again, let AN and BN both be convergent sequences. Then the sequence converges to A. The sequence of the product, A and BN, converges to the product of the limits, AB. Again, our proof begins with an arbitrary positive epsilon. Our goal is to show that there exists a natural number, and for every little n greater than or equal to that natural number, the absolute value of the difference, A and BN and AB, is less than epsilon. So maybe it's not so straightforward as before, and only straightforward because we've proven things in that style a few different times already. We have to be a little tricky in how we add 0. We're going to add 0 by adding AN times B and subtracting AN times B. Okay. Then we could take these two terms, rather this first term and the third term, put them together and factor out AN. We could take the second term and the last term, put them together, and here we can factor out a B. All right? Hopefully you see where we're going with this. That's arbitrarily small. That's arbitrarily small. A triangle inequality at some point is going to be called in for help. But of course we have these things added. Of course we shouldn't worry too much because, well, B is just some number. Now AN we might think of as a moving target, but in fact we can bound AN. Well, how do we know? Well, the entries of AN are that is, they belong to a Cauchy sequence, and a Cauchy sequence is bounded. We've proven that. So let alpha be a bound for the absolute value of AN. Of course, we know such a thing exists because, again, we know that every Cauchy sequence is bounded. So I can bound the absolute value. So let M be the larger of the two values, the bound for AN or the absolute value of B. Only two numbers, one of them has to be bigger than the other, unless they're equal, in which case M is equal to both of them. Now, since AN converges to A, there exists a natural number, let's call it N1, for which if little n is greater than or equal to N1, I'm guaranteed that AN minus A, an absolute value, is less than epsilon divided by 2m. All right, remember, I can make it less than anything I want so long as it's a positive number, and epsilon divided by 2m is a positive number. How do I know it's a positive number? Well, m is greater than alpha, greater than or equal to alpha, which is greater than or equal to the absolute value of an infinite number of numbers, which is greater than or equal to 0. And the absolute value of B is also greater than or equal to 0. Right? In fact, it's strictly greater than 0 because alpha is greater than 0. So this is a positive number. and this difference can be made smaller than it so long as little n is bigger than n1. Of course, since Bn converges to B, we can do the same trick. There's a natural number n2, and if little n is greater than or equal to n2, the absolute value of the difference between Bn and B is less than the same positive number, epsilon divided by 2m. As before, let little n be bigger than both of those natural numbers, n1 and n2. In fact, we'll call the larger of n1 and n2 n, big N. Let little n be greater than or equal to big N, then an bn minus ab is equal to, well, we already showed that is equal to this, right, by adding 0 quite cleverly. Then the triangle inequality says this is less than or equal to this. Now, I know that this term here is less than or equal to epsilon over 2m, and this term is less than m. This term is also less than m, right? Because remember, m was the max of either the absolute value of b or the upper bound of the absolute value of an. Both of these terms are less than epsilon over 2m. M divided by m, they cancel. I get half an epsilon plus half an epsilon, which is a whole entire epsilon. So we showed that there does in fact exist a natural number n. And if little n is bigger than it, this difference is less than epsilon, and epsilon is arbitrary. So we've proven our result. Theorem. This one concerns division. Now, we have to be careful in division because you can't divide by 0. Not even Chuck Norris can do that, even though they say he can. It's an urban legend. He can't. Okay. So let an and bn both again be convergent sequences, with the condition this time that bn does not converge to 0. So converges to some number b, but b is not 0. Then the sequence an divided by bn converges to a divided by b. Now the proof of that is, well, it's actually in your reading. You're assigned in your reading to read section 1.2 and 1.3 for this week. So the proof is there. And the proof is actually quite nice as presented in the book. So we'll just leave that proof there. And I would strongly encourage you to read both the proof of the theorem and the proof for the lemma that it uses very carefully. That's it for today.